so just to quickly go through this for Super Turtle. So after you've gone through and done all the calculations using the average speed and the acceleration of the object, what you're going to do is we're going to look at graphing the motion of this object. So you've got your chart paper. All you're going to do at the top is write velocity time graph for Super Turtle, as you can see there. So you're going to write that at the top of your sheet. You can pause this anytime you want as you're working through it. And we're going to set up an axis. So we're going to plot the velocity on the y-axis and the time on the x-axis. Now, to make this fit properly, just because I know the numbers, start 2 in and 1 up. That's probably the best spot to start, and draw a straight line to the top. Mark out every square as you see. On the x-axis, which is our time, we're starting at 0, 0 here. We're going to go straight across to the very end and mark out every 2. Now the scale that we're going to use, just because I know it's going to work for this one, is on the bottom. We're going to go every 2 squares is going to be 10 seconds. So we'll get up to about 110 seconds. The axis is time, and that's in seconds. Okay. Well, on the other axis, we're going to go up. Every unit is 10 meters per second. So we're plotting the time on this axis. Or sorry, this is the speed on this axis. There we go. I know that'll work out perfect because the maximum speed it ever reaches is 160, as you can find out from the things. Here, this is the velocity or the speed in meters per second. Good. So, the very first part of this, now let's get to actually graphing. In the very first part, Super Turtle started from rest and he accelerated for 40 seconds at a rate of 4 meters per second per second. I asked you to calculate the final speed. All of you would have calculated that the final speed was 160. So if the object starts at 0 speed at time equals 0, like so, accelerates for 40 seconds, which is to here, and reaches a speed of 160, we're way up here. So we can see the object's accelerating easily because what's happening is they start at 0 and they accelerate at a constant rate all the way up to 160 in exactly 40 seconds. Okay, so you're like, great, that's awesome. Well, what we do from here is we're going to figure out what the slope of this line is. So to find the slope, we know that the slope equals rise over run. And if we pick a couple spots, so we could pick here and here, we know that that has a rise of 10, 20, 30, 40 meters per second, and the run is 5, 10 seconds. Okay, so that's pretty clear. We know that the run here, sorry, the rise is 40 and the run is 10. 40 divided by 10 gives us 4 meters per second and that is exactly the acceleration from the question. In the question it said that Super Turtle accelerated at 4 meters per second. So what we know from a speed time graph is that the slope gives us the acceleration. On a distance time graph, the slope gave us the speed. On a speed time graph, the slope gives us the acceleration. That's a key concept. Very, very important to recognize. Secondly, it says calculate the average speed. So part C of this question says find the area underneath the curve. Okay, well, how do we do that? Well, all we're going to do is we're going to draw a dashed line down, like so. And there we go. Now it says find the area. Well, we have a triangle here, like that. The height of the triangle is 160, so area of a triangle is base times height divided by 2. Okay, the base is 40 seconds, so we put in 40 seconds. The height is 160 meters per second, and we divide it by 2. Well, look at this. 40 times 160 is 3,200. Sorry, and then divided by 2 gives us 3,200. The seconds cancel out, and we're left with meters. So this is the area, is 3,200. Well, it turns out that this is exactly the displacement that we calculated before. It's the displacement. So therefore, the displacement of the object during this time is 3,200 meters. That's a key concept. So it turns out that for speed time graphs, the displacement is just the area that's bounded by the motion. That's it. Okay, for part 2, Super Turtle was going 160. And then it says he decelerates at 2 meters per second for 30 seconds. How far does he travel in this time? So you have to do, step 1, step 2, step 3 to get to that. So what we're going to do is we're going to see that he's going to go 30 seconds, and for 30 seconds, if he decreases at 2 meters per second every second, that's going to give us a 60 meter per second delta V. And so all of you had found that if we decrease in those 30 seconds, so it takes us up to 70, we're going to be going only 100 meters per second at that point. And there we go. And again, we find the slope. Well, the acceleration is the slope. So our delta V over delta T, the rise over the run. Well, the rise is, we've dropped 60, so it's minus 60 meters per second, and the time interval was 30 seconds, which gives us negative 2 meters per second, which matches exactly what we had before. Okay, now it says find the area. A little trickier because we've got two shapes. Now, when you did the calculations by hand, just using the formulas, you found that the total distance during this time period was 3,900 meters. So what we're going to do is break this into two parts, like so. And the first part is a triangle right here, and the second part is this rectangle. You have to include both parts. So at the top, area 1 is base times height divided by 2. The base is 30 seconds times the height, which was 60 meters per second, divided by 2. 180 divided by 2 is, 1800 divided by 2 is 900 meters. So that's area 1. Area 2, base times height, that's it. It's just length times width, base times height. We've got 30 times, and that's only 100. From the bottom up to here is 100. Oops. Gives me 3,000 meters. So the total area is area 1 plus area 2, which is 900 plus 3,000. So therefore the displacement is 3,900 meters. And remember, that's because displacement is the area. So since we found the area, that's the displacement. So we know that during this part of the motion, this 30 seconds of time, he's traveled 3,900 meters. 900 of it comes during this, deceleration, and then the other part from here. Okay. The next part says he moves at a constant speed for 20 seconds. Well, constant speed, 20 seconds is right here. Doesn't change the speed. Slope's easy for this one. The acceleration, delta V over delta T, equals 0. There's no slope. It's not accelerating. So finding the area for this section is pretty straightforward. Just go like this, and we say the area equals length times width, which is 20 times 100, which is equals 2,000. So the distance it travels during this trip, 2,000 meters. And if you look at your notes for the calculations, it matches exactly. All right, the last part comes to a screeching stop in just 2 seconds. Or sorry, stop in 10 seconds, sorry. So that takes us down to the 100, like so, and we drop it down. Now, were we to find this acceleration, you guys, when you used your calculations, you found that the delta V over delta T, since it's negative, we're doing 0 minus 100, that's minus 100 meters per second, divided by the 10 seconds, is negative 10 meters per second. The distance it travels is the area of a triangle, so it's the base, which is 10 seconds, times the height, which is 100 meters per second, divided by 2. So we just go 100 times, that's 1,000, divided by 2 is 500 meters. So if you add up this distance, this distance, this distance, and this distance, that tells you the total distance that they traveled. You must show all those calculations whenever you're doing problems like this. So the key to learn from this is that the slope equals acceleration on a velocity time graph, and that area equals the displacement on a velocity time graph.